Hello everyone. In the series of Learning Database Management System, our today's topic is Armstrong's Axiom or Inference Rule. So first to understand this is a new term. What is an axiom? And before starting this lecture, let me tell you, prerequisite for this particular topic is functional dependency. I have already uploaded the video on functional dependency. If you have not gone through those videos, please first check those videos for better understanding of this topic. So let's understand what is the meaning of this axiom. So basically this axiom is a statement that is taken to be true and serve as a premise or standing point for further arguments. So what is the axiom? We will consider this as true and then we will further do all the logical calculation. So Armstrong axiom is used to generate the closure set. Fine. This Armstrong axiom, it was introduced by William W. Armstrong, and because of his name it is known as Armstrong's axiom. Basically what we are doing, we are using this to test logical implication of functional dependency. That's why I told you that prerequisite for this particular topic is functional dependency. So consider like this, that if there is a set of functional dependency, let us suppose we are having the set of functional dependency as F, then the closure of this F will be denoted by like this. In the superscript we have to put a plus. So if there is a set of functional dependency F, then the closure of F will be F plus. Is the set of functional dependencies logically implied by F? What is the closure of this F? It is the set of functional dependency that are logically implied by F. And this Armstrong axiom are the set of rules that when applied recursively, it generate the closure of the functional dependency. That's why I have written here, they are used to generate the closure set. Okay. Now, the Armstrong axiom are the basic inference rule. They are the inference rule. Using these inference rule, we can derive additional functional dependency from the initial state. So basically it's doing nothing, it's just generating the closure set. Okay. Now, there are six rules are present. Few are known as basic rule or primary rule. So there are three types of primary rule. First let's see those three types of primary rule and then we will talk about another rules. So first rule, which is a primary rule, is reflexive rule. Now what reflexive rule says? It says that if y is a subset of x, if for any functional dependency y is the subset of x, so we are saying if y is the subset of x, then this rule says x will determine y. So according to reflexive rule, if y is a subset of x, then x determines y. Let's understand with the help of an example. So for example, if I am having the value of x as so 5 values I am having for x, right? And y is a subset of x, means y can take value only which are present here in x. So here I am saying y is having the value as p, q and r. Now what reflexive rule says, if y is a subset of x, then x determines y. Yes, if we will take the closure of x, I will be easily getting p, q, r. X will functionally determine y. There is no issue in this rule. Fine. So hopefully this rule is clear. What reflexive rule is saying, if y is the subset of x, then we can say x determines y. This is your first rule. Now, second primary rule is augmentation rule. So this is your second rule, augmentation rule. Now, what this rule says, it is also known as partial dependency. In augmentation rule, if x determines y, so what we are saying, if x determines y, then xz determines yz for any x. So for augmentation we are saying if x determines y, and if there is any particular attribute z, so we can write xz also determines yz. Okay, now understand this with the example. So if I am having a relation, here I am having a relation R with elements P, Q, R and S. So these are the attributes I have for this relation R. Now what we are saying if P determines Q, if P determines Q, then for any particular Z, so here if I write PR determines QR, it's not wrong. Fine. For any particular Z, this can happen. Okay. So this is augmentation rule. Next, the third rule which we have is transitive rule. Okay. Now, in transitive rule, if x determines y and y determines z, if we are having a functional dependency like this, if x determines y and y determines z, then x must determine z. So this is very simple rule. If x determines y and y is determining z, then I can easily say that x is determining z. There is no issue in this rule, hopefully. So these three are known as primary rules, and these primary rules, why they are primary rules? Because other secondary rules can be derived from these primary rules, but these primary rules we cannot derive from any other rule. That's why they are primary rules. And because they are reflexive, augmentation and transitive, in few books the primary rules for Armstrong axiom you can get as RAT. R for reflexive, A for augmentation and T for transitive. So these are the primary three rules for Armstrong axiom. Now we have few secondary rules also, additional inference rule also, three additional more rules we have. So fourth one is union. Now union is same as we have studied in discrete mathematics and other subjects. Union works as the same as it works in other subjects. Union rule says if x determines y and x determines z, if x determines y and x determines z, then x must determine yz. If I write like this, there is no issue because it's a union. The same element determines y, the same element determines z. So I can easily write that x determines yz. Now, how I can write this? If you want proof, So you can check like this. What we are saying, x determines y and x determines z. It's given to us, right? Now if I apply on this, let us suppose this is my first expression and this is my second expression. Now if I will use augmentation rule on the first expression, for any z it should be true. So let me check for any x. If I'm using augmentation rule on expression number 1 with x, so what I'm doing, I'm applying augmentation rule on expression 1. I'm applying augmentation rule on expression 1 with x. So if I'm applying augmentation, what will happen? Xx determines yx according to this. For any z, if it is possible, then for any x also it's possible, right? Xx, same element, xx is nothing but what? X. So x determines yx, right? So this is my third equation. Now again, if I will apply augmentation on second expression, I am applying again augmentation on second expression with y. So let me apply augmentation rule on second one. On second expression I am applying now, on expression 2. Now this time I am applying with y. Okay, so what will happen when I will do this? If I will apply on the second expression, what is the second expression? X determines z. Fine. So if I am applying this rule with respect to y, then what happened? I can write this like this. Let me keep it like this so it will be visible. So I'm applying augmentation here. So can I write the fourth expression like this? Xy determines yz. What we have done here, I am applying augmentation on this second one with respect to y. So xy determines yz. Same thing I am writing here. Xy determines yz. Fine. Okay. Now this we are denoting as the fourth expression. Okay. Now using both third and fourth expression, if you can see, what is the third expression? X determines yx. Fourth expression says xy determines yz. Now yx and xy, they are one and the same thing. So basically what's happening? X determines xy, xy determines yz. So using transitive rule, if you can see here, transitive rule, can I say when x determines y, y determines z? So what we were saying? X determines z. So here what is happening using third equation? X determines xy. Similarly, xy determines yz. So using both third and fourth, I am applying transitive here. So I am applying transitive, and can I say x determines xy now? I applied transitive on third and fourth. Fine. So here if you can see, that's why they are known as secondary rules, because this is derived by the earlier rule. We have used augmentation and transitive to prove union. Fine. So if you can see here, what we are saying, if x determines y and x determines z, so we can say x determines yz. And for proof, I have proved that by using augmentation and transitive, we can prove that x will determine, sorry, here y, z. X will determine y, z. Okay. So the fifth rule which we have is decomposition rule. So the fifth rule is decomposition rule. Now your decomposition rule is reverse of union rule. What your decomposition rule says, that if x determines y and z, if x determines y and z, then x determines y and x determines z also separately. So how I can write this? Instead of this statement, I will write if x determines yz, then x will determine y and x will determine z also separately. Now how we are saying this? What is the proof for this? If we want to check the proof, how we can check what we are saying? The given expression to us is what? X determines yz. They are saying this. Let's prove that this thing is happening. Fine. So if I will use the reflexive rule, if you can see the first rule, reflexive rule. What reflexive rule says? If y is the subset of x, then x determines y. So if I prove this, that the y is the subset of x and z is the subset of x, I can prove x determines y and x determines z, right? So using first rule, let me prove. If I will take this expression 1, I am taking this expression 1, and what we are proving, that y is a subset of yz, right? So if y is the subset of yz, so can I write that yz will determine y, because y is the subset of yz. Here according to reflexive rule, if y is the subset of x, x will determine y, right? Similarly, y is the subset of yz, so we can write yz determines y. How we are doing this? Using rule number 1, which is reflexive rule, right? So using rule number 1, I am writing yz will determines y. This is my second expression. Okay. Now here if you can see, using both first and second, if I will use first and second and I will apply transitive rule on this, if I will apply transitive, x determines yz, yz determines y, can I write x determines y using transitive rule? Transitive rules also says the same thing, right? What transitive rules is saying, if x determines y, y determines z, so you can write x determine z. This is the transitive rule. Fine. Now using this rule, same thing we are getting here. X determines yz, yz determines y, so we can set x determines y. Now here same thing I can do. If I will write with respect to z, z is the subset of yz, so if I am writing here yz determines z using rule number 1, if this is my expression number 3, then can I write, if I will apply transitivity, use, if I am writing yz determines z with this expression using expression 2, so if I again apply transitive, I will use first and third now. So can I write x will determine z as well? So here decomposition is proved. X determines y also and x determines z also, right? So last we have pseudo transitive rule. So this is our sixth rule. Pseudo transitive rule. Now what this rule says? This rule says if x determines y and Wy determines Z, then we can say that Wx will determine Z. So how we can prove this? How we can check whether this is saying, what it is saying is true or false? What is given to us? It's given that X determines Y. This is my expression number 1, right? Next, what is given to me? Wy determines Z. This is my expression number 2. These two things are given to me. Now, if I apply augmentation on expression number 2 with respect to W, fine. So, sorry, let's apply augmentation on expression number 1 with respect to W. So, what will happen? If you can see here, augmentation, if we can say what augmentation is saying, if X determines Y, then for any Z, XZ is determines YZ. Fine. So I'm doing the same thing. I'm going to do same thing, and I'm applying augmentation on expression number 1 with respect to W. So what I will get using augmentation on expression 1 with W. So what I will get? Wx determines Wy. Fine. Now this is my third expression. So if I will use third and fourth expression, sorry, second and third expression, if you can see, Wy determines Z, Wx determines Wy. Again, transitive, Wx determines Wy, Wy determines Wz. So using transitivity on second and third, what I can write using transitivity? That Wx will determine Z, which we wanted to prove, if you can see, right? So hence proved that if I will apply augmentation and if I will apply transitivity, we will say that Wx will determine Z. So these were your Armstrong axiom, the inference rule, which we are going to use in further normalization. So I hope this topic is clear to you. Thank you.